morning, everyone. Good afternoon. Today we have our second Stanford speaker and the first student this semester, Jacob Andros. He's a second-year PhD student in our department. He joined us in fall 2022, and he is working under the direction of Dr. Bukhanayodi Raj. Jacob's research interests include Bayesian parametric statistics, methods, environmental and spatial applications, parallel computing, and uncertainty quantification and machine learning. He has been very active in his research in his undergrad and master's degrees, and he is continuing doing cool stuff. Thank you.
Yeah, thanks, Valerie. So second year PhD student, this is going to be my first time speaking really in any capacity at Texas A&M. But the project, the title of our project, of our research is Robust Distributed Learning of Functional Data from Simulators Through Data Sketch. That's a lot of big words. That's okay. We're going to try to tackle every little part of this title. And I know with the quick turnaround from the class being in here before us that we are a little bit shorter on time than the typical class window. So I'll try to move pretty quickly. But the first thing I want to address before even going into my presentation is just this phrase, distributed learning. How many people have heard that phrase, distributed learning? Okay, like half of you. Okay, so how many of you have heard of the phrase parallel computing? Probably more. Great. Okay, perfect. So parallel computing is this idea that you have a computer, like a central machine, and that computer has multiple cores, and each core can perform a task on its own simultaneously. So maybe your computer has 4 cores. You've got core 1, core 2, core 3, core 4. And say you're running an MCMC sampler and you want to run 4 different chains. So you can use different starting values, or for whatever reason. You can have each core perform sampling for a particular chain, and by the end of this, you've got 4 chains worth of samples in the amount of time it took to sample 1 chain. That's parallel computing. It's really neat. Distributed learning takes this a step further and said, okay, well, what if instead of using separate cores on the same machine, what if we literally have multiple different machines, say in this case, 4 different machines, and one is located in Dallas, and one is located in Houston, and one is located in Austin, and then one is located here in Bryan College Station, for example. And so you've got literally 4 different computers, 4 different machines, completely separated, and you're carrying out distributed learnings when you're carrying out some task, start to finish, on those completely separate machines. That includes the storage of the data, that's separated, you're starting the model fit, and you're not really combining or aggregating inference until near the very end. So that's distributed learning. I just wanted to give a brief intro to that before I dove in. Let's see. There we go. Okay, so now I want to give some information on the functional data part of this title. So we're slowly chipping away at this long, nasty title. Let's talk about functional data and specifically Gaussian processes. So some of you may be familiar with Gaussian processes. A typical Gaussian process regression model might look something like this, where you've got x beta, just as your standard regression coefficients. You've got your epsilon term, your error term, that's just your random noise with variance tau squared. And then you've got this W term, which follows a Gaussian process centered at 0, in our case in 0, it doesn't necessarily have to be the 0 function. And then having some sort of covariance kernel, which we call C theta, and that might be based on theta as well as sigma squared. Okay, so what's the challenge with this? If you're running some kind of MCMC sampler, you're going to have a covariance matrix C theta that is n by n. And each time you want to invert that, that's going to incur the computational cost of O n cubed. Same thing for storage. If you want to store that matrix or hold on to it until the next iteration, that's going to be n squared. So this is fine if your n is equal to 100, 500, maybe even 1,000, might be pushing it, but you could do it. It gets a lot tougher if your n is 5,000, 10,000, 50, 100,000, 100,000 cubed. That's a really difficult inversion to make. And there's a few things that have been proposed and set forth to address this. One of them is commonly known as, well, informally known as divide and conquer. more formally called like partitioning or data partitioning or something of the like. And that's when you take y and x, your data, your response variable and your explanatory variables, and you randomly divide them up into a bunch of different data sets, say k distinct subsets, and you just fit the model to each subset independently. And you can do that in a distributed framework on completely separate machines. And now you've reduced the size of each data set from n to roughly n divided by k. Speeds things up a lot. Another one is random compression, also known as data sketching. So now we're covering this last phrase in the title. So we've covered maybe half of this really long title. Random compression or data sketching, which is where you use a random compression matrix, so an m by n matrix, and you pre-multiply y and x by that m by n matrix, and you're essentially compressing their dimensions from n to m. And so in practice, your m would be much less than n. Sorry, I'm trying to pronounce these letters as best I can because it's really important, the difference between m and n, but they sound very similar. So you're compressing the dimension, the length of y and the dimension of x to m rows. Yes, for sure. So y is n by 1, x is n by p. B, this matrix is m by n. So if I pre-multiply these, the new matrix, py, will be m by 1, and x, px, will be m by p. Does that help?
And m would be smaller than n.
And yes, and m has to be small. Well, it should be much smaller than n, otherwise there's no point to doing this. So if n was, for example, 10,000, you might consider making m 100. We'll talk a little bit more about that later.
The distinct subset overlap or non-overlap?
Overlap meaning containing the same data points.
Yeah.
They should all, so no, there should be no overlap. They should be completely, it's a partition. You're partitioning the data, so no overlap. Good question. Any other questions?
What kind of random
We'll talk about how it's generated in a few slides, but it's follow like each element of phi is like follows like a normal centered at 0 with variance 1 over n. So it's random and following a normal distribution. No, they would not. It's a full partition, so there would be no overlap. Yeah. So all of y, x, and your locations in space are all sent to one and only one data center. Okay, so both of these, divide and conquer and random compression. So one other thing I should mention about random compression is you can use multiple phi matrices. You might be saying, well, phi is a really arbitrary matrix. You're just randomly generating it, and that's true. But you can generate k different phi matrices. And you can get k different sets of phi y and phi x and fit them all in parallel or in a distributed framework. So both of these methods leverage distributed learning to their advantage. And distributed learning has become kind of a buzzword in recent years, especially with the increase in massive data sets and the need to be able to fit models to them in reasonable amounts of time. Okay, additional benefits of both these methods, of both divide and conquer and random compression, include data confidentiality or privacy. So with divide and conquer, you are splitting up your data and storing all the subsets in different locations. And while this doesn't fully protect the entirety of the data necessarily, it does diversify the risk. So if one data center is broken into or leaked, only a subset of the data is being leaked. With random compression, it's even a little bit stronger in that, and there's a lot of theory behind this that I won't go into today, but you're transforming the data in such a way that it is not possible to recover the original y and x from phi y and phi x. And even if the phi matrix is known, there's still conditions where it's impossible to do that. Okay, so now I'm going to pivot and talk about an application, particular case study that really motivated this work. So I'm going to give you the background on this, and then I'll return to this whole data compression thing, and we'll talk about how it ties in. So for those of you who are from back east or know your geography, you might remember that New Jersey has this little tiny peninsula on the southern tip of it. So this here is Wilmington, Delaware. Right here would be Baltimore and DC. Up here would be Philadelphia. This here's the southern half of New Jersey, and not much goes on there because like most of New Jersey, you think of being near like Philadelphia or New York, but this is all just like beaches and access to the ocean. And this particular peninsula is very exposed to storms that come up this way through the Delaware River, and so it's prone to flooding. And what more is that there are various power stations located on this peninsula, and if a storm is coming with certain characteristics, it's useful to know, okay, how likely is each power station to receive this amount of water accumulation? And if they receive more than, 4 feet or so of water, then we might need to shut it down before the storm hits. So this right here is the peninsula of interest. This right here is an example map of the water level that occurred at each point on that peninsula after a particular storm. And this analysis was attempted just last year, but it was not attempted using a random compression framework, and that's what I'm going to be talking about today, is that random compression framework and how it can apply it here. So the issues to address with this data set, what makes this data set hard is first that it's really large. So N is about 50,000, just short of it. So you can imagine 50,000 cubed is something. It's really, really huge, and you're not going to be able to keep inverting that for 1,000, 5,000, 10,000 iterations of an MCMC sampler. The next thing is that the locations of the coordinates, I guess I should say the locations of the coordinates themselves aren't confidential, they're just coordinates. But the locations of the power stations are confidential, and so this data has need to be privacy protected. And we already know that both divide and conquer and random compression can address both of these things. But the last thing is that this analysis forces us to incorporate both fixed effects and random effects. So for those of you who are familiar with mixed models, typically they're called fixed and random effects. I'm going to refer to them more as local and global attributes. So location-specific predictors, local, and storm-specific predictors, global. What I mean by that is, so take elevation, for example. Elevation is a local attribute because every different point on this map has a different elevation above sea level, or I mean, they could be the same, but they all have unique elevations in that sense. Meanwhile, a global predictor would be something like velocity of the storm. And there are multiple storms in the data set, but for each storm that comes in, say storm velocity, if storm 1 comes in, every point on this map is subject to that same storm. So the storm velocity predictor is the same for all 50,000 points on this map. But then, of course, when a new storm comes in, that storm velocity and other storm-specific predictors will change. So that's what we mean by local and global attributes. And that's what this analysis is going to force us to incorporate, which is something that has not really been done or worked with a whole lot yet. Okay, so how are we going to incorporate these storm-specific predictors? Well, suppose that we weren't worried about these global storm attributes. Suppose we were just worried about elevation, and that was our local predictor. Then the likelihood function would look something like this. It would be the response variable y, and this is before random compression. I'll bring that in a second. Our response variable y would follow a normal distribution centered at x beta and with a variance of sigma squared times our covariance function plus tau squared times the identity. So now we're going to formulate the likelihood as a product of all likelihoods for each storm. So for storm S, there's capital S storms total. For lowercase s, that's the index of the storm. It's just the product of all likelihoods for each storm. And so YS is the water level for all locations resulting from storm S, and ZS is the storm-specific predictors. That's what's represented there. X is the elevation predictor.
S means the different types of storm or the.
So capital S is just the number of total storms in the data set, which was actually I think like 400, but we only had access to full information for a few of those, and we were trying to demonstrate how it works when you can only obtain a few simulations. So we used like S equals 10, like 10 storms.
That's not kind of confused. You
Sure.
mentioned that the storm is like a global feature.
Correct. So going back to this map here, so for each storm that comes through, so storm 1 comes through, it has a velocity of 30 knots. every single point on this map for that particular storm is subject to that 30 knots predictor. It's global to all points on here within that storm.
Cost of the storm is by time. This month a storm, next month a storm, next that.
Right. So then another storm might come through and have a velocity of 60 knots. And at that point, all these points are now subject to 60 knots as the predictor.
It's by time.
So it changes by storm.
The storms.
So
the
if you
same
think-
condition.
If you think of a mixed effects model where you have individuals, different subjects, the storms are your subjects. Does that make sense?
The different time of the storm.
Yeah, the storms are from, I don't even remember the time frame, from different times of the year, different years. But they're different storms, and each storm has its own, velocity and air pressure and direction and all those things.
So your predictors are characteristics about the storm, right? Fact, like that came in.
Yeah, velocity, air pressure, direction. There were a couple others dealing with like projected sea level and other things. Those are all your random effects, I should say.
And then this data product would be like a nice projection of water levels. Close to the
Sorry.
water or something.
Right here. So this is the YS is the water level for all locations for the S storm, for storm S.
Right, but like that's like over, it's like you have time where the storm's coming in, so it's just max project at the end of the storm. Like,
So the likelihood function is a product of the likelihood for all storms. Which in and of itself may not be super intuitive, but when you're using Metropolis Hastings and all you're looking to do is maximize your likelihood anyways, this does work. Does that help for now?
yeah, I think we're.
Okay, we can talk later for sure. Yeah.
That all storms affect all the territory at the same level. Is it just a simplification or?
It's not that they affected all the same, that's part of the, right. So at a given time, suppose tomorrow at noon, there's a storm that's going to hit New Jersey, and that storm is going to affect every coordinate differently. But that's part of what we're trying to understand is like, okay, a storm that comes in at 50 knots. Okay, these points down here are going to get hit really hard and have this much water level accumulating. And these points up here won't get hit as hard. These inland points here, the blue you see here, these aren't getting hit as hard, and the water's not going to accumulate as much. But it's all, yes, it's all subject to the same storm though. That storm will affect the different points differently, but it's all one storm hitting it at that time. It's not, at least for the simplicity of this data set, we aren't measuring storms where there's one coming in from the Atlantic and one coming in from Philadelphia and one coming from New York. Like it's one storm at a time. Okay. So we talked about the product of all likelihood functions, and now let's go into the actual model specification. So we have a few different parameters that we need to specify priors on. First, sigma squared and tau squared. We just did inverse gamma 1, 1. It's a relatively uninformative prior that allows us to traverse the space as much as we need. For beta, we gave it a normal prior centered at 0. That's the regression coefficients. And I should say both beta and gamma is probably what this should say. Beta is the coefficient for the local predictor, elevation. Gamma is the coefficients for the global predictors, so storm characteristics. And then the last one is theta, and I'll talk about this in the next slide, but theta is going to sort of in a way follow a discrete prior for this. So our likelihood before was the product of the likelihood for each individual storm, but this was not in the compressed framework. Now that we are pre-multiplying by the random compression matrix phi, this is going to look like, so for the storm S, it'll be phi ys follows a normal distribution centered at 1 dimension m chronocored with z, vs times gamma. So gamma is your coefficients for your storm specific predictors. And then plus phi x beta, that's your local predictor elevation. And then a covariance matrix that's just the same as before, but pre-multiplied and post-multiplied by phi and phi transpose. So that's just your basic linear models, variance of AX, pre-multiplied by A, post-multiplied by A transpose. And I think I mentioned this earlier, but phi, each element of phi is generated from a normal 0, 1 over n distribution. Okay, I'm not gonna, for the sake of time, I'm not gonna get super in the weeds on the actual sampling procedure, but in a nutshell, so sigma squared and tau squared, we use Metropolis Hastings. The nice thing is that the kernel of the covariance function, so we're gonna keep theta fixed for each individual run of the sampler. And so because theta is fixed, you only have to compute this phi transpose k phi once, and then you can keep using it throughout the sampler. You don't have to recompute it every iteration. So that's going to be subject to the Metropolis Hastings sampler. And then beta and gamma, you can actually get in closed form. They're full conditional. There's a normal distribution, and you can use a Gibbs sampler there, which makes that fast. But the nice thing now is that instead of incurring a cost of ON cubed when we do this, it's just going to be OM cubed, and M is much smaller than N. And this right here is where the substantial computational benefit really comes in. Now I mentioned that theta is fixed. So this is just kind of a visualization of overall how the distributed framework works. You've got your data, Y, this is all for a specific storm S, YS, ZS, and X. And these might be stored on different machines, but you're going to have those, you're going to choose a random compression matrix, phi1, for example. You'll pre-multiply YS and beta, that should say X beta. That should say X beta and not individually beta and X. But you'll pre-multiply phi1 by X and by Y. And then you'll also bring in a theta. So the way theta works is it's really computationally intensive to update theta at every iteration, because that means you have to recompute the kernel of the covariance matrix over and over. What we suggest, and that's what's been done before, is you choose a chain of theta values between, a plausible range, say from 10 to 100 or 10 to 20 or something. And you evenly space out those thetas on a grid, and you just use one for each chain of the simulator. Yeah.
What kernel are you taking?
So we typically use exponential. I don't bring that up in here because you could use others, but we in our simulations did exponential. Yeah. Anyway, so with theta, it's in a way it's like using a discrete prior, where you specify here's 10 or 20 values that we think theta could take on, and you're just plugging in one for each chain of the sampler. Speeds up computation a lot, and it's been done in similar studies, and so we felt like that was a shortcut we could take. So anyways, at the end of this, you're going to get all these different estimates. So from chain one, you might get a posterior for sigma squared, tau squared, beta, gamma that's different from the estimates for chain 12. And the way we aggregate those results to get one centralized inference is through the Wasserstein mean. And the Wasserstein mean is fairly straightforward. It's just the average of the quantiles. So for example, if you wanted a 95% credible interval, you need the 2.5 percentile, the 97.5 percentile. So the 2.5 percentile of your entire set of samples from all chains is just the average of each chain's 2.5 percentile from all systems that you ran it on. Same with 97.5. Same with if you want the posterior median, just take the mean of all the medians. So if you were using 20 different machines here, you would have 20 things to take the mean of for each quantile.
That's the last slide.
This one?
So for me, it's like a K1 corresponding to one a set of the Markov chains, like the MCMC samples. So for example, if capital H equal to 10, you have like 10 packs of the MCMC samples.
Yes, that's exactly right. Your H is the number of chains you're running, and H is restricted to however many machines you have available. Keep in mind, this all can be run as parallel computing. If you only have one machine, but you've got 20 cores, like you can run H equals 20 here. Yeah.
I think Wasserstein mean should be W squared instead of just W. And in that case, they will induce Wasserstein.
Yeah, that's what we denoted with the 2 subscript. It's a notation used from another paper.
Like, or did you do the square or?
You want just to find the optimizer.
I have to look at the notation we adapted from the other paper. I think the Wasserstein mean on its own is taken to include the square. Yeah.
Are you using the full data in each?
So no, so you're this is a little bit, this representation here is really a parallel computing framework, not distributed learning. If you were to split the data up and store it on different centers before doing any of this, then the full data would never be in the same place at one time. That's actually what I have on this slide. So in practice, and we didn't do this because we use the research servers here where you just have like, node Z13 and all 20 of its cores. But in practice, if you had 20 different machines or 20 different nodes, research nodes that you could store the data on, you could split each phi matrix accordingly and pre-multiply it by each subset of data on its own machine. And so you can avoid having the data all in one place at one time and reduce the storage cost as well. So there's both a distributed learning aspect to this and distributed storage, right? You're trying to address that O of n cubed as well as the O of n squared. Those are two big problems that you want to tame as much as possible. Okay, for the interest of time, I'll kind of skim through these simulations and then go to the results of the actual case study. So the simulations, we just wanted to simulate data from a Gaussian process that had known parameter values and run our algorithm on it and just make sure it worked. So, we use sigma squared equals 2, tau squared equals 0.2, beta 1 equals 2, beta 2 equals -1. And then we also had a gamma. I couldn't quite fit it all on one slide. The gamma was 5. And just as a sanity check, we just tried out some divide and conquer methods as well as our random compression method and found that, yeah, it generally works. We're estimating sigma squared pretty closely around 2 and tau squared pretty closely around 0.2, and the betas we do even better with. So that's just a quick sanity check to make sure that both the divide and conquer and our random compression approach are generally working, and that we can then attempt our random compression approach on the real data. Also, as far as choosing M goes, this is just a little visualization I made. You can get away with a really low M. Once you get to, at least this was this was N equals 10,000. We tried an M of, once you get to about M equals 100, your MSPE at the end is really just random fluctuation. It's hardly any different. So you can use, even if M equals 50, you're getting pretty much the same results here. If you try M equals 10, yeah, your MSP is going to be a little bit higher and it'll run really fast. But your M does not need to be that high. There's no hard and fast rule for how to choose M. But this is just one visualization that shows it. And if you choose M equals 100, you're running the algorithm in a substantially shorter time than if you use it M equals 500. Okay, so now to the results of the actual flood analysis. So this was one particular storm in our test data set. So we did a training test split. This was one particular storm. These are the true water levels for each location under that storm. And we use our methods of sketching or compression, as well as two contemporary competitors. So nearest neighbors Gaussian process and BAS, Bayesian adaptive spline surfaces, which is very recent, still kind of unexplored. And so you can see the nearest neighbors kind of under-predicted. It was a little more conservative. BAS was a little more aggressive in predicting the high water levels. Ours was a little bit conservative as well, but not nearly as much as the nearest neighbors Gaussian process was. And these water levels are all in meters, but the cutoff that the client was interested in was actually 4 feet, which is just a little bit more than a meter. So if your water level is over 4 feet, we want to shut down the power station. If it's not projected to be over 4 feet, we'll leave it running. And what's interesting is that as you look at these 3 competitors, including our own method, our MSPE wasn't the greatest. It wasn't as good as nearest neighbors Gaussian process, but our error percentage, meaning the percentage of locations that were correctly classified as over or under 4 feet, was actually really good, 6% better than the other 2. And then we have a few other measures here. Interval coverage you're familiar with. As far as uncertainty quantification, NNGP is not great. We also have interval score and energy score. And for the sake of time, I'll kind of skim past these, but basically interval score favors models with small prediction, narrow prediction intervals that still contain the truth. And then energy score is a formula that measures both your predictive accuracy, your point prediction accuracy, as well as the uncertainty involved. And then for one last sanity check, these are just posterior density plots of each parameter of interest. So you've got sigma squared, tau squared, beta, and then you've also got all the gammas, gamma 1, gamma 2, 3, 4, 5. So those are all the storm-specific predictor coefficients. And you can see that, you know, we can combine inference from all the different machines we ran this on. We can aggregate them with the Wasserstein mean, and we can plot posterior densities with posterior means and credible intervals, just like we would in any other framework.
Definitely to increase like age, what's the future? Like if you're doing random compression using by
Yeah.
like if you just use more random compression matrices and just duplicate this with more machines.
I mean, if it's a matter of like 10 or 20, because I ran this both with h equals 10 and h equals 20, and the results weren't that different. Now, I have to imagine if you ran h equals 2 or h equals 1,000, then you'd start to see a difference, but I haven't had the resources to actually empirically test what that would look like. I guess I could run it on h equals 2. I just didn't think to. But as far as like 10 versus 20, it's not too huge of a difference. I think these results were from h equals 20.
But like the difference between h equals 20 and h equals 200.
I suppose 20 to 2. I guess I'd have to empirically run it to see for sure, but at some point there's going to be diminishing change. You're right. I don't know exactly. I guess what I'm trying to say is I don't know exactly when that diminishing change occurs. If it's after 20 or after 100 or after 200, but in theory, at some point, it's not going to matter how many observations or how many subsets you split the data into, or how many phi matrices you compress the data with. Yeah.
So after you've done your random compression and you've split your problem up across your different machines, within that given machine, for its compressed data, it's fitting a full Gaussian process, not a.
So yes, it is fitting a full Gaussian process for this flood data problem. In our simulations, I don't have these results in here because I just need time to explain them. We also did a modified predictive process and a sparse Gaussian process. But full Gaussian process is kind of the default. Yeah.
That's why sort of even for relatively aggressive compression, you're still looking kind of for 2 hours.
Yeah. It's not like this stuff is running in seconds. This stuff is still taking, 1-2 hours, but the alternative is weeks. If you have n equals 50,000 and you're inverting that every iteration 10,000 times or however much. In fact, I think I tried it, and after a week they killed it. So at least a week. I don't know.
Just let's say you had like flood maps basically. Were these color balanced? Like is the color?
Yes, it's the same color scale on all. I had to set Z limits for the colors. Yeah.
So what's the difference of your random compression method and the divided?
Yeah, so both can be run in parallel or in a distributed framework. I guess the difference is that in divide and conquer, you're like the data. So the commonality is you can store the data all in different locations. In divide and conquer, you don't do anything with that data. It's stored in different locations. You just fit each model in each location and combine them at the end. With random compression, you are applying a transformation to each data set in each location and reducing the runtime even further.
Yes, but in divide and conquer, you also split the whole data into several subsets, and then you can always store each subset in each machine, and then you can also do all these top levels.
Correct. So both. I mean, they're more similar than they are different. They can both be. Everything can be done on separate machines. You don't have to aggregate anything until the end. There's very little communication overhead. Just the only difference is the actual compression from N to M in random compression. And I guess I should also add there's a little bit of confidentiality protection with random compression. So like with divide and conquer, you're diversifying the risk of data being recovered. But if one machine is accessed improperly, that's still one subset of data leaked. Whereas with random compression, if one machine is accessed, all they can access is compressed data, which is almost meaningless in and of itself. Does that make sense? Okay, so I'll try to wrap up in the next few minutes here, but really to sum up, and I know I didn't get to touch every little point of this project, but this distributed inference framework we have here, it's capable of both inference for both local and global attributes, so fixed and random effects. And that's really useful in a lot of environmental applications that have storm simulations. The lab we are working with, they have these simulators for other storms that are much more expensive to obtain simulations from. And you need to be able to work with, make use of just 5 or 10 simulations total. So it's capable of inference for both local and global effects. It's free of the census. So something I didn't really get to talk about because it was more with our simulation studies in here, is that when you do divide and conquer, there's some ambiguity as to how you divide the data, like how you subset it or partition it. Do you do a completely random partition? Do you do a stratified partition, like, stratified by subdomains? Do you do a full subdomain split? There's a lot of ambiguity as to how you choose that. And in fact, in our simulation studies here, where it says sub and str, that was a subdomain partition and a stratified partition. And like, you can see that the results were a little bit different. Like, for example, estimating sigma squared, your estimate was higher using a subdomain split than it was using a stratified split, and not immensely higher, but enough that the intervals didn't overlap. And you just, unless you're in a vacuum in simulation study where the true parameters of everything, you don't really have any index for what type of data split to use. So there's a lot of ambiguity associated with divide and conquer and how you partition your data, and we avoid that entirely with the random compression approach. Wanted to point out that this is resilient even in settings where you can only obtain a few subjects, a few storms. So like I was saying earlier, we had almost 400 storms available to us, but the whole point of this for being applied to other projects in the future is that most of these storm simulators are very expensive to get data from. And what if we only have 5 or 10 available? Can we still build an effective model off of that? And that's what we did here. And then really just the underlining of it all is this is a viable solution to reduce both the computation cost and storage cost in fitting Gaussian process models with really large data sets. And that's it. So thank you guys for being here, and I can continue to take questions.
I have a question. So you apply the random compression by multiplying random matrix.
Mhm.
And after you did this kind of transformation and conduct some other MCMC, will you reverse back?
We don't, and there's actually no need to reverse back because we are getting all the estimates we need. Let me go back to the right graphic. We're getting all the estimates we need from the compressed models, and we're aggregating those estimates. So the posterior medians and credible intervals of sigma squared, tau squared, beta, gamma, we're getting that all, and we have no need to go back to the original data.
The data has already been changed.
Correct. So I guess I should add a caveat. The only need we have to go back to the original data is for measuring predictive diagnostics.
Oh.
Measuring like.
As long as there's no prediction involved, like predict a time series like that, you do not need to reverse back to the original.
Well, we can, so in doing prediction, you as the model or the researcher, you have access to the full data. The purpose of compressing the full data is that it's harder for someone who doesn't have access to inappropriately access it. You as the researcher have the full data, and you can use that to do a check on, coverage or MSP or something that requires you to measure your model's prediction against the true value at each point. But we don't, I wouldn't say that we back transform. Like, we have the data, we compress the data. So we have the full data and the compressed data. We don't need to back transform because we already have the full data, if that makes sense. Is there a question back here?
I think told that the 10 completion matrix, the completion matrix elements are drawn from our So there is literature using sparse concept, right?
Yes, there is.
And this process them are whole sparse, both of them. I mean, the guarantee is whole for sparse and dense space.
So I didn't hear that last part.
I mean, instead of the dense completion matrix, you use sparse ones.
Yeah, that was one of, so in our simulations, that was one of the, and I didn't have room to include them here, but we ran, so, oh no, I did include them here. Oh, okay. So you have the full Gaussian process, modified predictive process, and then nearest neighbor Gaussian process, which is just essentially like a sparse approximation.
So, yeah, but I'm not saying about sparse approximation.
Okay.
You've chosen your elements and the compression metric.
Oh, you're talking about generating the phi matrix.
Yeah.
Gotcha. I have not explored super in depth the different ways to do that. I know there are multiple, and this is one we decided on, but there are definitely what you're talking about, ways to zero out more elements of the phi matrix.
Because
Yeah, there is literature on that.
drawing a bunch of problems.
Yeah. Yeah, there is literature on that. Although I will say the generation of the phi matrix really is not like a computationally intensive step relative to everything else being done. But there absolutely is literature on
So
that.
I would say performance difference, but it's okay.
Oh, gotcha. Yeah, this is the only phi generation method we used here. Yeah.
You go to the slide.
Yeah, where was that? Here.
So, sorry, what did you repeat? What was the initial size of the data?
I think it was, so the initial size was 10,000. N was 10,000. And this was M equal to, I think we started at 10. I want to say, or maybe it was 5, 10, 25, 50, 100, 200, 300, 400, 500. So there's kind of diminishing returns after like 100.
So, yeah, I guess my question is, do you have any intuition on what kind of data I can do to this compression model? Because the multiplication by the random matrix, you're just taking all of your observations and turning them into, all your new observations are random observations.
Yeah, I will say the main restriction, when you say what kind of data, you mean like what size of data?
Or like, could I do this on any kind of data set?
I would imagine so. So Raj has done a lot this similar work for a lot of different regression settings and things like that. He would know more than I do there. But it's like, as far as the size of the data set, the only thing you're restricted by is you have to compute the full distance matrix once and only once. And actually you can circumnavigate that as well if you store the data on separate machines. But like in our example where we were using the research server here, we had to compute the full covariance matrix once. With n equals 10,000, it wasn't bad. With 50,000, it took a few minutes. If you had like n equals 1,000,000, you pretty much have to resort to distributed storage before you can do anything else.
At the beginning of the talk, you mentioned this is a functional data.
Mhm.
Why is it called functional data?
Just Gaussian like I suppose this could be applied in a variety of functional data settings, but the one specifically we examined here was the Gaussian process. And full Gaussian process, modified predictive process. So a few different kinds of functional data, but all fitting within that Gaussian process setting.
Right, we run out of time, but thank you very much for very active discussion.